This video will cover the input and output image tables of the SLC 500 PLC. This is the rack we'll be looking at. It's different from the one you'll be using for your lab. That's on purpose to help you practice finding inputs and outputs in a processor. Since engineers like to start counting with 0 instead of 1, this first slot is slot 0. The processor for a SLC is always in slot 0. After slot 0, cards can be placed anywhere you want as long as the I/O configuration is set up correctly so that the processor knows where each input and output is. Our small rack simply has 2 input cards and 1 output card. On the left is the power supply. It doesn't have an address, it's just giving the DC power to the processor. As mentioned, slot 0 is the processor. Here, slot 1 is this input card with its inputs going to different field devices, switches, etc. Slot 2 is another input card as well. And slot 3 is our output card. We'll get into more of these in detail. I have a blank program with the I/O configuration already set up. I've downloaded it to my processor and I'm online. For any information on how to do that, please review the first video in the series. Our file window on the left has a lot of information for us. It has information about the controller. This is where we set up our I/O configuration. We can look at the properties of the controller. We have our different ladder files that we'll be getting into. We have the input and output image tables, which is what we'll be looking at. It also has tables with information about timers and counters. And we have integers, which are just words of data that we can use for different values. And other information, address and symbol lists, instruction comments, run comments, different things that we can access and change through the file window. We're going to go ahead and double click on the input image table. Remember that on our processor, slots 1 and 2 were input cards. So on our input image table, the address shows us that the 1 here represents slot 1 and the 2 represents slot 2. So this part of the address reads I for input, colon, slot 1, word 0. Since these input cards only have 1 word of input information, there's only 1 word of data here. Here, we actually have the address, I colon 1 bit 0, just the way we would write it, just the way the processor wants to see it. When I open the window up, it gives us even more information. We've got a syncing input and a sourcing input. We'll get to those in later lessons. You'll notice I have a 1 in the 2's place here, and I have a 1 in the 4's place here. That means whatever input device is connected to these is making a contact or making these bits true. So if I change to decimal, I can actually see those words in decimal form, 2 and 4. But we're going to use binary because then we can see each individual bit. This highlighted bit, you'll notice when I put my arrow over it, the address comes up as well, so I can see that address. I colon 1 bit 0. The selector switch right position is just a note that I had put in earlier in this program and deleted it out, but that description is still in there. Input bit 0 is connected to the right contact on this selector switch, so that if this switch were in the right position, bit 0 would be true. Right now, bit 0 is false and bit 1 is true, and that's what my input image table is showing me. Bit 0 is false, bit 1 is true. If I flip my selector switch to the right position, bit 0 is a 1 and bit 1 is a 0. I know that sounds kind of weird, but we can see that bit 0 is true and bit 1 is false. As we address these bits, whatever device is connected to that terminal is going to make that input or that bit true or false. I have a push button at bit 2. The setup on this box is bit 0, bit 1, bit 2, bit 3, and then there are other inputs connected elsewhere. So if I look at my input image table and watch bit 2, when I press the button, I'm now pressing the button, I get a 1 at that bit. When I let go, I get a 0. And by doing this, I can discover what address each device is connected to. Without knowing this information, I would not be able to write a program. As mentioned, when I press the button, I get a 1 at bit 2. And right now I have a 1 at bit 2. And I have a 1 at bit 0 because my selector switch was in that right position. I have a 1 at bit 2 and bit 0. You may notice that as I make a switch or let go of it, it takes 1 to 2 seconds for that bit to change states. So be patient with it. Inside the PLC, the state is changing immediately. However, remember that the personal computer is just monitoring the information that it gets from the PLC. So the update rate for the screen is low priority to the processor. Running its outputs and program are what's important. So now I'll take a look at the output image table, and they're all zeros. I have 3 lights connected to these first 3 bits. With the inputs, we could just press the button and watch for the change. With the outputs, we have to highlight one of the bits, make it a 1, and press enter. And you may have heard the click. That click was this first light turning on. This light is output bit 0. The output modules have output bit indicators very similar to the input module. Also, you'll notice if we open the window, we have a little bit more information on our output card. It's a relay output card, which just means the card has sets of contacts that are going to close for each output. You'll notice here the output is in module 3, so that makes the address for this bit O for output, O:3 bit 0. You'll also notice, and it's the same on the inputs, that when I put my highlighter on any one of these bits, the indicator down below changes to show me what my address is. So right now, I have a 1 at O:3 bit 0. I'm going to make that a 0 and turn my light off. I'm going to go to the next bit, O:3 bit 1. Make it a 1. And my light is lit for that output. I'll make it a 0. Make bit 2 a 1, and I think you're kind of catching on how this works. This light here is O:3 bit 2, which is the one that I just made high in my program. I'll make it a 0 to turn it off. The setup of your PLC rack is different because for the first lab, you will do the same thing. You'll open the input image table, press the different buttons, make the different bits true and false so that you can figure out which inputs they are. You'll want to make a list. The lab will have you make a list so that as you're writing a program, you don't need to try and figure out each bit every time you need it. You want to take that couple seconds and make a list to write it down. Same with the outputs. You'll open up that output image table. You'll make one of the bits true so that you can see which light turns on your station, and you'll be able to write a program. In future labs, you're going to be writing some more complicated programs. So I'm going to show you a couple of tips to use as you start writing these. I'm going to go offline first. We want to go offline to do our programming. It's just asking me to save. You'll hear me say in programming, save early, save often, save with a new name. You can always back up if you've saved your work. However, if you've been working for 2 or 3 hours on a program and then the power goes out, which happens, you will lose all of your work because you didn't save it. And you will not receive any sympathy from your instructors because you will have been instructed in your lab to save your program and to save it with a new name so that you could retrieve at least your latest version of your work. I've got my blank program. I need to add a rung, as we did in the first lab. I'm going to put an instruction in. As we showed you in the last video, if I double-click that question mark, I'm going to get a little window. If I put I in that window, the word input comes in. If I double-click the word input, it's going to show me virtually that same information from that input image table. It's showing me that I have 2 input cards. I have one in slot 1 and I have another one in slot 2. Well, since we've identified our selector switch and push button as inputs on slot 1, I want to use that module, so I'm just going to double click on that module. And what the software does is brings up the next available unused bit. Since I haven't written a program at all, bit 0 has not been used. If I simply press enter, my address is already written for me. This one happens to already have a description. Yours will probably come up like this. So you will want to put a description that makes sense. Without using up too much time. Selector switch right position. And that's my new description. I'm going to put in an output. This is exactly what we did in the first video. I'm going to double click on the question mark. Here I want an output. So I'm going to press O for output. Double click the word output. I only have one output card. You'll probably have a couple. You'll notice the next available bit is already brought up. Hit enter. This one also has a previous description. I'm going to rewrite it. Green light on the top. So now, let's say I want to make this green light turn on only if my selector switch is in the right position and I press my green push button. So I'll bring down another input. I will double click the question mark, press I for input, enter. Now you'll notice the next available bit is bit 1. But if you remember when we made our list from our input image table, bit 1 is the left position of that selector switch, and I want the push button which was bit 2. So I can just go ahead and enter that bit 1, but now I want to modify that and take that out, take the 1 out and put in a 2. So now I can enter green push button description. So now I have a basic AND circuit. Let's say I wanted another rung of logic, and I wanted that same selector switch in the right position. As with any Windows product, there's several different ways I can do things. I could double-click the question mark, press I, enter, get the next available bit. It wouldn't be bit 0, it'd probably be bit 1, and I could modify it just like I did for the green push button. However, if I just come up and grab the 0 and I bring it, you'll notice the address itself is coming down with it, and I didn't have to type that bit in again. I just grabbed it from here. Now you can't, if you grab the whole instruction, you'll get the whole thing. Well, that's probably not what you're going to want. So I just deleted that. So here we have our selector switch in the right position. So let's say I want a different light to light up. Let's say I want the second light down, which was bit 1, which was the orange light. Now, I can also bring up my output image table, and since I made a list with the bits, and I know that bit 1 is my orange light, I can come over here and I can grab the bit from the image table, drag it over to my instruction. You notice the little red handle on the instruction has to turn green, let go, and the orange is, the description orange was in there from before, a different program I wrote. So let's say I want the orange light to be lit if the selector switch is in the right position or the green push button is pressed. As you'll learn in the logic portion of the next unit, to put something in an OR position, I have to have a parallel branch. To do that, I just highlight some part of the rung, whether it's the end or an instruction, and this here branch rung, come down here, and you'll notice I'll get the green handles. It's going to show up just on one side. I have to grab one side and pull it because the software doesn't know exactly what I want to branch around. There could be several instructions on that line and it doesn't know. So I can put my AND condition in here, and let's say I want the green push button. Again, I can just grab the bit, or I could type it in or grab it from the image table. So now I have two logic rungs. As mentioned, you'll be learning a little more about logic in the next unit. If the selector switch is in the right position and the green push button is pressed, the green light comes on. Here I have, if either the selector switch is in the right position or the green push button is pressed, I'll get the orange light. So I'm going to go ahead and verify my program. Verify, down on the bottom it says verify has completed, no errors found. I'm going to go ahead and download my program. Change back to run mode. It's going to ask me if I want to go online. Yes. So now the selector switch is in the right position, so both of these instructions are true. If I turn my selector to the left, they both go false. If I have my selector in the right position and I press the green button, I get the green light at the top. If I'm not making the green push button, it'll go out. You'll notice that while the selector is in the right position, the orange light is also lit. If my selector switches to the left, I don't have my orange light. If my selector switches to the right, however, if my green button is not pressed, my green light will not be lit. However, because I have the orange light in an OR circuit with the right selector switch, the orange light is lit right now. If I turn the selector to the left, these two bits go false and my orange light turns off. However, if I now press the push button, I will get the orange light. Now, these two instructions are the same input bit, so this instruction is true. However, because the previous instruction, the selector switch, is false, my output will not be true, only my orange light, because this has two different paths for the continuity to flow through. In your lab, you will program some similar circuits. However, your input and output structure will be different. But all you have to do is open those input and output image tables to discover where those inputs and output bits are connected to out in what I call the real world. Thank you.